Okay, so the last video got cut off, so I'm just gonna start again. So we have our reference circle, and please watch that video first because my pictures are not going to be equal to the animation that they were able to do there. So what we're going to do is we have this object circling on, say, one of those old-fashioned turntables, and we have some sort of screen or film or something that's recording this over here. And so we have this object like you saw in the video just circling around in uniform angular motion, which means a constant angular speed, W, right? But when we look at this projected in simple harmonic motion, our velocities will not be constant. So let's take a look at why that would be. So right here in the center, that's supposed to be the center, we have our equilibrium. And when we have a full radius, like right here, that is going to be projected as our, what we call it, negative A. And over here will be our positive A. So you might think, well, that's the same everywhere. And it is. But as you look at an object going around like so, we're going to do a couple of, let's do 3 different vectors here. I've got v sub t tangential velocity here, tangential velocity here, and tangential velocity here. Now, of course, we could do it at any point in the circle, but you're going to get the idea. And then we're going to look at centripetal acceleration, which, as you recall, is always toward the center of the rotating motion. Right? Okay. And so as we look at this, what we can see projected on the screen here is here, we can break this vector down into, well, either vector can break it down into x and y, or depending on how you're looking at it, this could be the x and this could be the y if this were on top, and vice versa. Well, the point being is we could break these vectors down. Okay? And so what you can see here is that you have projected a maximum x, okay, or maximum negative x. But as you go around like this, so I'm looking at that point tangent right there, you do not get, if you look at this, you do not get a full x. All you get is a partial x. And as I come up closer and closer here, I'm only going to get a little partial, okay? And I know I'm doing it vertical here. Just turn it upside down, or the other way, or rotate it 90 degrees, and you get that. It would be your horizontal. And as you get right here, as you see this, it's like you're at equilibrium, and x is 0. Displacement is 0. So you can see it does change on the screen. And then as you come up like this, it changes and changes and changes until you're here where x is at a maximum. Okay, and so when x is at its maximum, our velocity is 0. But when x is 0, our displacement is 0, our velocity is at a maximum. So a couple of things I want you to notice here. First of all, with the velocity, what you're going to find at equilibrium. So we could look at any point, but let's look at equilibrium. At equilibrium, your velocity is at a maximum. So think about this just as a vector. More of that is being projected. Velocity is at a maximum here where x is 0. You're at the equilibrium point. Notice one other thing. So maybe I should jot that down. Notice one other thing too with energy, because work and energy is an important concept, and it has been for a while now. At equilibrium is at a max. Okay. You can also think of our example with a person going through the center of the earth too. This is the same type of question. X, our displacement, is 0. Okay. We're right at equilibrium. And the last thing that I want you to take a look at is that we do not have any, if this were a spring, we wouldn't have any of that. What we would have is that it's been transferred all to that. The energy is all kinetic energy at this point. So if we were to translate this idea to a spring, what we'd see is that there's no spring energy here. It's all velocity. at equilibrium. Now, at negative a and positive a, the reverse of this is true. X is at a maximum, the velocity is at 0, and we don't have any kinetic. We have all 1/2 kx squared. So make sure that you understand what's going on there too. With acceleration at equilibrium, okay, a sub c is 0 at equilibrium, right? At equilibrium, look at the vectors here. A sub c, if I was trying to project that onto the screen, it would be a dot, right? However, right up here, when our maximum acceleration, or sorry, our maximum amplitude, our full x, our full displacement, our a sub c is at a maximum up there, whereas at equilibrium it was 0. Okay, and just understanding that idea with this reference circle is an important thing. You can do a lot of problems with this. I don't think we're going to do a lot of problems with it. But as you can see, you could break this up and use trig to calculate certain values at certain points. But again, I don't think we're going to be doing that.